Hi, my name is Anjali Patel, and today I'll be presenting my Raspberry Pi TCP port scanner for CNIT 176. So this project demonstrates how a small Raspberry Pi can perform real cybersecurity and networking tasks, specifically scanning device on a network to detect open ports. Here is a quick overview of what I'll be covering within this presentation. This includes the business case or rationale behind the project, the Raspberry Pi architecture used, the setup and build procedures, results and demonstration, troubleshooting I encountered, and finally the lessons I learned in relation to CNIT 176. So, for the main purpose of this project was explore a low-cost and portable device like the Raspberry Pi can be used for network security operations. Organizations often need tools to scan their own networks for open ports or misconfigurations. Port scanning is a really common cybersecurity task, and doing it on a Raspberry Pi makes it lightweight, energy efficient, and easy to deploy anywhere. So the business case shows that this type of scanner can be useful in security labs, small businesses, classrooms, or even as part of a larger security toolkit. So for the architecture, I focused on there was 5 Raspberry Pi components that were essential for this project. The first would be the ARM CPU. So the ARM CPU handled all the processing for the scanning logic and the multi-thread. Second would be the RAM. It supported running multiple threads at the same time without slowing down. The third would be the network interfaces. So Wi-Fi was the most big one. These were required for any kind of port scanning activity because the scanner has to attempt TCP connections to other devices. The fourth would be the micro SD card, which stored my operating system, my Python script, and the log files. And finally would be the operating system. In this operating system, I used Raspberry Pi OS that was built into the Pi itself. It provided Linux networking utilities, Python libraries such for socket and threading, which my script depended on. Now for my architecture diagram. So within this diagram, it highlights 3 main hardware areas I used. So the middle we have is the CPU, and then we have the micro SD card, which stored everything, and the CPU was the brain of this whole project. And then lastly would be the Ethernet, which is where the networking took place. So here I provided was me SSHing to my personal computer to Pi. So the procedures I followed. To begin, I installed Raspberry Pi OS on a micro SD card and booted the Pi, which was already installed. Then I enabled SSH so I could work remotely from my laptop, which made development much easier. I also updated the Pi using apt-get and installed the packages for my Python that I needed, which would be Python 3. After that, I configured my network settings, created a project directory which is called port scanner, and tested connectivity using commands like ping and if command. This made sure the Pi was correctly connected to my local network before building the scanner, and as mentioned, and I will mention it again, I struggled with this and the troubleshooting as well. So now we have a live demo. I have 2 videos provided. So the first video is going to be me running it, and then the second video is going to be the log files and where the results are stored. Here's the first. Okay, and now here's the second video. So, with the results and demonstration, explanation, and documentation behind this, so the scanner obviously was successful in detecting open ports. Uh, it was successful, and once again, you can use this on any IPv4 device. It prints out the results to the terminal in real time and also writes them to a log file. The log file part I showed in the second video, and the terminal would be it can be printed out two ways in the terminal that I made. The first way would be a it's called like a terminal user interface. It interacts with the user itself, so it gives like enter choice, and then you enter the first one, and then you are given a set of instructions based on the user having to install or write those out. And then lastly would be through the terminal itself, where the terminal will run it automatically. Because of threading, the scanner performs significantly faster than a single thread implementation. It runs within 5 seconds. So the results demonstrate accurate identification of open ports like 22 and 443 and closed ports as well. So this proves the Raspberry Pi can handle port scanning just like a regular computer, but with much lower power usage. So now for the building. For the build process, I wrote a Python script that uses the socket library to attempt connections to different ports. I used threading to make the scan significantly faster, since without threading, the script would scan ports one at a time, and as I mentioned, it would be 5 seconds. I implemented a loop to cycle through a range of ports, and each port scan was handled on its own thread. I also added logging so that results were stored in a text file for later review, which was shown in the second video once again. Then I tested the script using devices on my network that had known open ports, and once again, that would be 22 for port 22 SSH or port 443 for HTTPS. Finally, I ran full scans on local devices to validate that the scanner was accurate. Now for the troubleshooting. I did encounter several issues that I had to troubleshoot. One problem would be SSH access failing, as I mentioned earlier. Sometimes the Pi's IP address would change, so I had to run a lot of hostname minus I, a ton, on the device to reconnect. Another issue involved socket errors in Python when connection attempts timed out. So I fixed this by adding a lot of try and except blocks and adjusting timeouts constantly. Performance was also slow at first because I was scanning ports one at a time as well, so adding threading helped the scan speed dramatically. So this project helped me understand how the Raspberry Pi handles networking tasks and how Python threading can improve performances. I also learned that it's very important when using SSH and Linux commands for managing a remote device. Troubleshooting taught me a lot about error handling and testing networked code. And if I were to improve this project, I would create a graphical user interface or integrate Nmap to make the scanner more robust. But overall, the project really strengthened my understanding of both IT architecture and cybersecurity practices. So, how does this relate to CNIT 176? So, this project directly relates to CNIT 176 because it implies the core concepts of information technology architectures using the Raspberry Pi. And by building a TCP port scanner, I used the CPU, RAM operating system, networking interface, and storage in one integrated system. The project demonstrates how the Pi's architectural components work together to run multi-threaded Python code, establishing TCP connections and log results. It reinforces networking concepts, hardware/software interaction, and system performances, which are all key learning outcomes within CNIT 76. So I would just like to say thank you so much for watching my presentation.